I'm Yanle Lu, and I'm a PhD student at Cornell University. Today I will present our project named A Numerical Study on the Non-Local Effects of Urban Form in the Lower Atmosphere, Implications for Urban Climate Modeling. First, I will talk about the motivation. From the left picture, it's for Chicago. We can find that there are many tall buildings located at the center of the urban area, and as we go from the center to the urban fringe, the mean building height decreases. However, in the right picture, which is Beijing, China, the buildings are lower around the center and there are taller buildings as we move from the center to urban marginal area. There can be several tall buildings near the center, but here we are seeing in the mean height perspective. There are several possible reasons. Near the center of the urban where the city developed from, there might be historical sites and also many low-rise buildings from years or decades ago. And as we move to the suburban, due to the large population in China, there are many high residential buildings. However, in America, a lot of townhouses and lower residential buildings around the city. Therefore, if we consider the mean building height of the urban area, we will have these two kinds of very different profile. This difference may influence the exchange of heat and momentum between urban area and the above atmosphere boundary layer, and therefore impact the weather and climates. Also, it may influence some characteristics in the urban area and rural area. However, this cannot be captured in many mesoscale models. They always use a simplified urban canopy model with several parameters, but not considering detailed urban forms, such as the height variation, and this could lead to large uncertainties in prediction. Therefore, we want to investigate the non-local effects of different urban forms. The main research questions will be how do the non-local effects change among different kinds of urban forms? And what are the zones of urban influence in the upwind, downwind regions and vertical direction? And the model we use in this study is a turbulence resolving model called large eddy simulation. It directly computes large-scale motions and parameterizes the subgrid scale terms. And the governing Navier-Stokes equation for filtered quantity is shown here. All the terms are resolved filtered quantities like the velocity. And the tau is the deviatoric part of the subgrid stress tensor, and F is the body force applied to the domain, and B is the immersed boundary force representing the action of the obstacles on the fluid. And this is the scalar conservation equation. Theta represents resolved temperature, and Q is a subgrid scale heat flux. Then as for the domain setup, 6 arrays of cubic buildings with 3 different types of streamwise inhomogeneity are considered. The mean building height for all cases are same, but the height of the buildings varies in streamwise direction according to 3 different types. And we call it case hill, case flight, and case valley. At the same time, this design has guaranteed that they have the same surface area to volume ratio. And there are 36 grids in vertical direction and represented by symbol LZ, and LX and LY represent the streamwise direction and spinwise direction. Prescribed pressure gradient is imposed to the domain as I said before, and the boundary condition for the domain is horizontally periodic, and we apply no-slip bottom boundary condition and stress-free top boundary condition for velocity. For temperature, we apply constant heat flux on all surfaces like the ground, wall, and roof, and zero flux at the top of the domain, and we'll start from the neutral condition for now. In addition, because of the horizontally periodic boundary condition, the repeated occurrence of buildings in streamwise may influence the judgment of horizontal impact region of urban area. Therefore, sensitivity tests are conducted to explore the effects of the streamwise domain size, in which Lx is elongated to 8 times of Lz, and all the other settings remain same. All the simulations are run to reach the statistical steady state first, and then collect and analyze the data. First, we show the distribution of velocity field to get some sense of the similarity and difference among three cases, and also check the sensitivity of the domain size. This is a mean streamwise velocity, which is averaged on time and spanwise direction. The axes are normalized by the mean building height h, and the structure for streamwise velocity above the urban domain is indicated by the block castle contour length. As we can see, Case Flight and Case Hill both have one trough in the domain. However, Case Valley has a shallow trough here and followed by another deep trough. As for the mean vertical velocity, Case Flight and Case Hill are also similar and both have one upward deflection and downward deflection in the domain. The only difference between them is that the dividing position of the positive and negative vertical velocity in Case Flight is more downwind than Case Hill. However, Case Valley has two positive and two negative vertical velocity centers. To summarize, the Case Flight and Case Hill show similar velocity fields characteristics. However, Case Valley shows apparent different features. In addition, the results for the sensitivity test domain remain similar to the original setup, which means Lx equals to 6 times Lz is sufficient for the simulations. Then we start to identify the zones of urban influence and first go with the downwind direction. In order to quantify the horizontal extent of the urban area, in other words, the impact region, we consider the concept called momentum deficit. It means the loss of the momentum associated with the drag exerted by the buildings on the ambient flow, and is always assessed by velocity deviation. And we use a metric called scaled streamwise velocity, which is defined by this equation. The bar means the time average and the angle brackets means spatial average. And subscript represents at which direction we take this average. Therefore, this is the spanwise average and is a function of x and z, while this is the horizontal average and is only a function of z. And the contour shows the relative velocity deviation. The horizontal extent is determined by the location where the scaled velocity changes signs. And the dividing line are shown in the figure. Case Flight and Case Hill also have similar performance, while Case Valley has a longer impact region. Similarly, scaled temperature is also computed to analyze the influence in terms of heat, which shows similar characteristics. Another thing I want to point out here is that there is a more obvious high temperature region in Case Hill between the middle and the end of the urban area, since we impose same heat flux boundary conditions for all the cases. And this feature may indicate that the ability of Case Hill to transport heat is not as good as the other two forms. It's only a conjecture and we will further explore it. Then we analyze the zones of urban influence in vertical direction named the vertical extent. The first method we used is the Money-Nabokov similarity. The main assumption is that the starting height is an indicator of the vertical influence of urban form. I won't go to details due to the time limit. We apply least square regression for this formula for different starting heights, and as we can see, the best fit height is around 2h for three cases, which indicates that the vertical extent is almost the same for different cases. The result for non-urban area is just shown for indicating the local influence caused by buildings in the vertical direction. In addition, the almost identical profiles further prove that the horizontal extent we defined earlier is reasonable. To increase the robustness, we also consider another metric called blending height. Based on the definition, it can be visualized by this formula. We can see that there are large effects of the buildings to the local area and the area just above the canopy. And as for the blending height, the estimation is identical for all cases, which is consistent with results given before. In other words, even though their local influence may be different, the influence on the atmosphere above the urban extends to a similar height. To summarize, here are several preliminary results for now when we examine the non-local effects of different urban forms. As for the future work, here are the plans to better understand the impacts of different urban forms and find better representations for urban forms.